The closest star to Earth has a name. It is only 4.24 light-years away. Astronomers call that distance next door. But here is what nobody tells you. That next-door neighbour sits 25 trillion miles from where you are right now. The farthest object humanity has ever launched, travelling at 38,000 miles per hour every single second of every single day, would need over 75,000 years to get there. That is longer than human civilization has existed, and that is the closest star, not some distant speck across the galaxy, the nearest one, the one scientists call our neighbour. What you are about to discover will permanently change the way you understand the word close. The distance to the nearest star is the most terrifying number in astronomy. If you are someone who enjoys having your sense of reality completely dismantled and rebuilt from scratch, do me a favour and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives into the universe. Now, let's begin. There is a phrase astronomers use when they talk about the nearest star. They call it our stellar neighbour. They describe it as right next door. They speak about the closest star system as though it were a house down the street, a familiar address just around the corner from our cosmic home. The language is warm, approachable, almost friendly, and it is one of the most misleading descriptions in all of science. The closest star system to Earth is called Alpha Centauri. It is not one star but three, locked together in a gravitational relationship that has lasted for billions of years. Alpha Centauri A is the largest of the trio, a yellow star slightly bigger and brighter than our Sun. Alpha Centauri B is its companion, a slightly smaller orange star orbiting alongside it. Together, these two stars circle each other once every roughly 80 years, bound by mutual gravity into a binary pair that from Earth's southern hemisphere appears to the naked eye as a single bright point of light. But there is a third member of this family, and it is the one that matters most to this story. Orbiting the central pair at an enormous distance is a tiny, dim, red dwarf star called Proxima Centauri. It is so faint that you cannot see it without a telescope. It is so small that it contains only about 12% of the Sun's mass. It barely qualifies as a star at all. And yet Proxima Centauri holds a distinction that makes it one of the most important objects in the night sky. It is the closest star to our Sun, the nearest stellar neighbour in the entire Milky Way galaxy. The one object beyond our solar system that sits closer to Earth than any other star among the 400 billion that populate our galactic home. Proxima Centauri lies 4.24 light-years from Earth. When you hear that number for the first time, it does not sound frightening. 4.24. It sounds manageable, almost small, a number you could write on a napkin, a figure that fits neatly into a sentence without requiring scientific notation or breathless superlatives. Compared to the scale of the galaxy, which stretches 100,000 light-years from edge to edge, 4.24 light-years seems like nothing. A rounding error. A cosmic inch. But that feeling of comfort is an illusion created by a unit of measurement most people have never truly unpacked. A light-year is not a unit of time. It is a unit of distance. 1 light-year represents the distance that light travels in a single year, moving at 186,000 miles per second. Not per hour, per second. Light crosses the entire width of the United States in less than 1/60th of a second. It reaches the moon in 1.3 seconds. It arrives at Mars in a few minutes. Light is so fast that for most of human history, scientists debated whether it even took time to travel at all. Some believed it was instantaneous. It is not. And when you multiply its speed across an entire year of non-stop travel, the distance it covers becomes staggering. 1 light-year equals approximately 5.88 trillion miles. That number is already difficult to process. 5.88 trillion. If you tried to count to 5.88 trillion at one number per second, it would take you over 186,000 years, longer than modern humans have existed. And that is just 1 light year. Proxima Centauri sits at 4.24 of those. Multiply 5.88 trillion by 4.24, and you arrive at roughly 25 trillion miles. 25 trillion. This is the distance separating you from the closest star in the universe beyond our sun, the one astronomers call our neighbour, the one described as nearby. 25 trillion miles of empty space, standing between Earth and the nearest point of stellar light outside our own solar system. To understand why this number is so much worse than it sounds, you need to feel how distance works inside the solar system first. Because inside our solar system, the numbers are large, but they are survivable. They fit within a framework that human minds can stretch to accommodate. The Sun sits roughly 93 million miles from Earth. That is a big number, but we have built an intuition for it. Light covers that gap in about 8 minutes and 20 seconds. When you look at the Sun, you are seeing it as it appeared 8 minutes ago. A slight delay, barely noticeable, nothing that disrupts your sense of the Sun as a close and immediate presence in your life. Move outward, and the distances grow. Mars at its closest approach comes within about 34 million miles of Earth. At its farthest, the gap stretches to roughly 400 million miles. We have sent spacecraft to Mars. We have landed rovers on its surface, flown helicopters in its thin atmosphere, photographed its canyons and craters in extraordinary detail. Mars feels like a place we know, a destination within reach. The journey takes about 7 months with current propulsion technology. Long but achievable, a problem engineers have solved. Jupiter sits about 484 million miles from the Sun on average. Saturn is roughly 890 million miles out. Uranus floats at about 1.8 billion miles. Neptune, the farthest major planet in our solar system, orbits at an average distance of approximately 2.8 billion miles from the Sun. We have visited every single one of these worlds. Voyager 2 flew past Neptune in 1989 after a 12-year journey from Earth. The spacecraft sent back photographs that revealed Neptune's deep blue atmosphere and its great dark spot. Even at that extreme distance, human technology reached out, made contact, and brought back images that expanded our understanding of the outer solar system. Now, go farther. Push past Neptune and into the Kuiper Belt, the ring of icy bodies that includes Pluto. New Horizons reached Pluto in 2015 after a 9.5-year flight, covering roughly 3 billion miles. That mission represented one of the longest targeted journeys in the history of space exploration. The images it returned showed Pluto's heart-shaped nitrogen ice plain in breathtaking resolution. Even at the edge of our planetary neighborhood, humanity managed to arrive, observe, and report back. The distances were immense but not impossible. Here is where everything breaks. The farthest point any human-made object has ever reached is currently occupied by Voyager 1, launched in 1977. After nearly 5 decades of continuous travel at approximately 38,000 miles per hour, Voyager 1 is now roughly 172 astronomical units from Earth. 1 astronomical unit equals the distance from Earth to the Sun, about 93 million miles. So Voyager 1 has covered approximately 16 billion miles since it left Earth. That is an extraordinary achievement. It is the single greatest distance any product of human engineering has ever travelled. And in November of 2026, Voyager 1 will reach a historic milestone. It will become the first human-made object to be 1 full light day from Earth. That means a radio signal travelling at the speed of light will take 24 hours to reach the spacecraft. A full day just for a message to arrive. Another full day for the response to come back. The round-trip communication time will be 48 hours. But here is the number that changes everything. 1 light day is roughly 16 billion miles. Proxima Centauri is 25 trillion miles away. Voyager 1, the farthest thing humanity has ever sent into space, after nearly 50 years of non-stop flight, has crossed less than 1/15 of 1% of the distance to the nearest star. Read that again. Less than 1/15 of 1%. 50 years of travel at 38,000 miles per hour. And the nearest star has not gotten measurably closer. Voyager is not even a visible speck on the road to Proxima Centauri. It is a single footstep on a journey that stretches across continents. And that journey leads to the closest star, not a distant one, not a star on the other side of the galaxy, the nearest one. This is the moment where the word close begins to collapse. Inside the solar system, distances are measured in millions or low billions of miles. The jump to the nearest star multiplies those numbers by a factor of thousands. It is not a gentle escalation. It is a cliff, a wall, a discontinuity so sharp that the entire framework of distances you built while thinking about planets and moons and asteroids becomes instantly useless. Nothing in your solar system experience prepares you for the scale of the gap between our Sun and its nearest stellar neighbour. The two regimes of distance, interplanetary and interstellar, are not on the same spectrum. They belong to different categories entirely. Consider it this way. The distance from the Sun to Neptune, the outermost major planet, is roughly 2.8 billion miles. The distance from the Sun to Proxima Centauri is roughly 25 trillion miles. That means the nearest star is approximately 9,000 times farther away than Neptune. 9,000 times. If the entire solar system out to Neptune's orbit were compressed into a single inch on a ruler, Proxima Centauri would sit 750 feet away. You would need to walk the length of 2.5 football fields just to reach the nearest star on that scale, while the entire known solar system fits beneath your fingernail. This disproportion is not something the human mind naturally grasps. Our brains evolved to process distances we could walk, distances relevant to survival on the plains of Africa, a few miles to the nearest water source, a day's march to the next camp. These are the scales our neural architecture was optimized for. We can stretch our comprehension to include things like cross-country flights and satellite orbits. But even those demands push against cognitive limits. Interstellar distances do not push against those limits. They obliterate them. 25 trillion miles exists in a realm of numbers where intuition simply switches off. The Alpha Centauri system, all three of its stars, orbits the center of the Milky Way galaxy just as our Sun does. Both systems travel at roughly similar speeds through galactic space. The two systems are not flying apart at tremendous velocity. They are relatively stable neighbours in galactic terms, maintaining a distance that changes only slowly over millions of years. Proxima Centauri is actually moving very slightly closer to us. In about 26,000 years it will reach its closest approach to our solar system, narrowing the gap to around 3.11 light-years. After that, it will begin drifting farther away again. But even at its closest future approach, the distance will still measure roughly 18 trillion miles. The nearest star will still be thousands of times farther than Neptune. The gap will still be functionally infinite by any human standard. What fills that gap is perhaps the most unsettling part of the entire picture. The answer is almost nothing. The space between our solar system and Proxima Centauri is not a crowded highway connecting two busy ports. It is a desert, a vacuum. An emptiness so thorough that it makes the voids between planets look practically congested. Inside the solar system, there are objects scattered throughout, asteroids in the belt between Mars and Jupiter, comets in the Kuiper belt, countless small icy bodies drifting through the outer regions. There is structure out there, material to encounter, gravitational signposts that mark the territory as belonging to our Sun. Beyond the Kuiper belt lies the theorized Oort cloud, a vast shell of icy bodies that may extend from roughly 1,000 to 100,000 astronomical units from the Sun. The Oort cloud represents the outermost boundary of the Sun's gravitational influence. Objects this far out are so loosely bound to our star that passing stars can nudge them out of their orbits entirely. The Oort cloud, if it exists in the form scientists predict, would take Voyager 1 roughly 300 years to reach at its inner edge and approximately 30,000 years to cross entirely. Even at its outer boundary, The Oort cloud is still only about 1.6 light-years from the Sun, not even halfway to Proxima Centauri. Beyond the Oort cloud there is nothing, no gas stations, no gravitational assists from nearby planets, no material to collect or resources to use. Just light-years of vacuum containing a scattering of hydrogen atoms so sparse that you would find only about 1 atom per cubic centimetre. Now imagine you are inside a spacecraft crossing this void, not reading about it, not looking at a diagram, actually inside a vessel somewhere between our Sun and Proxima Centauri, years into the journey, with years still remaining. What would you experience? You would experience nothing. Out the window, stars would fill the sky in every direction, roughly the same stars you see from Earth, arranged in roughly the same constellations. This is one of the cruelest features of interstellar travel. At the distances involved, even years of continuous motion produce no visible change in the star field. The constellations do not shift. The destination star does not grow brighter. The sun behind you does not noticeably dim. The sky looks the same on day 1000 as it did on day 1. There are no landmarks, no signposts, no way to perceive your own motion through the void without consulting instruments. A traveller gazing out the window mid-journey would have no intuitive sense of progress whatsoever. The universe would appear frozen in place, as though the spacecraft were sitting still in an infinite room full of distant, unchanging lights. This is fundamentally different from any journey humans have ever undertaken. On Earth, travel produces constant sensory feedback. The landscape scrolls past. Cities appear on the horizon. Coastlines resolve out of haze. Even in space within the solar system, there are reference points. The Earth shrinks behind you. The Moon drifts past. Mars grows from a dot to a disk. The Sun shifts position relative to the background stars. There is always something changing, something confirming that you are moving, that the destination is getting closer, that the effort is producing results. The interstellar void offers no such confirmation. It is a journey through a space so uniform and so vast that the human senses cannot distinguish motion from stillness. You are hurtling through vacuum at tens of thousands of miles per hour, and the universe gives you nothing back, no feedback, no reward, no evidence. The psychological implications of this are rarely discussed in technical assessments of interstellar travel, but they are profound. Human beings are not designed for environments without change. We require stimulus, variation, a sense of progression to maintain cognitive health. Solitary confinement in a featureless environment is one of the most psychologically destructive conditions known. An interstellar crossing would impose a version of that condition lasting not days or weeks but years or decades. The void outside the spacecraft would be unchanging. The interior of the spacecraft would be confined. The crew, if human, would need to sustain motivation and mental health across a journey in which the only evidence that anything is happening exists in the abstract readouts of navigational instruments. The destination would be a number on a screen, ticking down with agonizing slowness, offering no sensory confirmation that the end is approaching. The interstellar medium is not just physically empty, it is experientially empty. It is a space that provides nothing to a traveller except time, silence, and the knowledge that both the origin and the destination are too far away to matter in the present moment. For comparison, the air in the room where you are sitting right now contains roughly 25 quintillion molecules per cubic centimetre. The interstellar medium between here and Proxima Centauri is emptier than any vacuum that has ever been created in a laboratory on Earth. It is space in its most literal and terrifying form. A void so complete that it challenges the very idea of there being anything between here and there. This emptiness has practical consequences that extend far beyond abstract discomfort. Any spacecraft attempting to cross this gap must carry everything it needs for the entire journey. There is no resupply, no mid-course correction using a planetary gravity assist, no slowing down by dragging against atmospheric particles. The spacecraft must launch with all its fuel, all its power, all its shielding, and maintain itself across a crossing that would last thousands or tens of thousands of years with current technology. Every system on board must function without maintenance for longer than any civilization in human history has survived. The engineering challenge is not merely difficult. It lies so far beyond current capability that it exists in a different category from any engineering problem humanity has ever solved. The light-year gap between our solar system and Proxima Centauri also distorts time in ways that make the distance even more psychologically oppressive. Light is the fastest thing in the universe. Nothing with mass can travel at or above its speed. This is not a technological limitation that might be overcome someday. It is a fundamental law of physics confirmed by every experiment ever conducted. The speed of light is not a barrier we have not yet broken. It is a boundary woven into the structure of space-time itself. And even light, moving at 186,000 miles per second, needs 4 years and roughly 3 months to travel from Proxima Centauri to Earth. When you look at the night sky and see stars, you are seeing ancient light. The photons entering your eye from Proxima Centauri left that star over 4 years ago. You are not seeing the star as it is. You are seeing it as it was before the last presidential election, before the last Olympics. The star you observe is a time-delayed image, a ghost from the recent past projected across 25 trillion miles of vacuum, and Proxima Centauri is the closest star. The light from more distant stars in our galaxy has been traveling for hundreds, thousands, even tens of thousands of years before it reaches your retina. Every star in the night sky is a postcard from the past. None of them show you the present. This delay means that any form of communication between our solar system and the nearest star system would operate on a minimum 8.5-year cycle. A message sent from Earth at the speed of light would arrive at Proxima Centauri in 4 years and 3 months. A response sent back immediately would arrive at Earth 4 years and 3 months after that. The fastest possible exchange of information between here and our closest stellar neighbour takes longer than most people spend in high school. A single question and answer, sent at the maximum speed the universe allows, would span nearly a decade. Conducting a conversation at this rate would require patience measured not in minutes or hours but in lifetimes. Inside the solar system, these delays exist but remain manageable. A signal to Mars takes between 4 and 24 minutes, depending on orbital positions. A signal to Jupiter takes roughly 35 to 52 minutes. Even the signal to Voyager 1, approaching 1 full light day, represents a 48-hour round trip. These are long waits by everyday standards, but short enough that mission control can actively manage spacecraft. Commands can be sent, responses evaluated, corrections issued within a working week. None of this applies once you cross into interstellar space. The nearest star imposes communication delays so severe that real-time interaction becomes physically impossible. Any probe we send would need to operate with complete autonomy. Any signal we receive would describe conditions that existed years before the message arrived. The universe enforces isolation at the interstellar scale with a thoroughness that no technology can circumvent. The Alpha Centauri system itself is a fascinating place that makes this isolation feel even more cruel. It is not a barren collection of dead stars. It is a dynamic system with confirmed planets and active scientific interest. Proxima Centauri hosts at least 2 confirmed worlds. Proxima Centauri B is an Earth-mass planet orbiting within the star's habitable zone, the region where liquid water could theoretically exist on a planet's surface. It was confirmed in 2016 and represents one of the most tantalizing exoplanet discoveries ever made. A rocky world, roughly the mass of Earth, orbiting in the habitable zone of the nearest star to our Sun. If you were designing a target for humanity's first interstellar mission, you could not ask for a more compelling destination. Proxima Centauri D, a smaller world roughly 1/4 of Earth's mass, was confirmed by the new NERPS spectrograph at La Silla Observatory in 2025. It orbits much closer to its star, completing a full orbit in just 5.1 days. It is too close and too hot for habitability, but its confirmation demonstrates that the Proxima system contains multiple worlds. Meanwhile, a previously proposed third planet, Proxima Centauri C, appears likely not to exist based on the same near-PS data, which found inconclusive evidence for the signal originally attributed to it. And it is not just Proxima that holds secrets. In 2024 and 2025, the James Webb Space Telescope found strong evidence for a candidate gas giant orbiting Alpha Centauri A, the largest star in the system. If confirmed, this Saturn-mass planet would orbit in the habitable zone of a Sun-like star just 4 light-years away. It would be the nearest planet to Earth orbiting in the habitable zone of a star similar to our own Sun. Follow-up observations in February and April of 2025 did not redetect the candidate, but orbital simulations showed that in half of the possible orbits, the planet would have been too close to its star to be visible during those windows. The confirmation attempt continues, with the next observing opportunity expected in August of 2026. These discoveries pour salt into the wound of interstellar distance. The nearest star system is not boring. It is not a dead zone with nothing worth visiting. It is a multi-star system harboring confirmed planets, including at least one rocky world in a habitable zone, and a candidate gas giant around a Sun-like star that the most powerful telescope ever built is actively trying to confirm. The cosmic real estate next door appears to contain exactly the kind of worlds that would justify the greatest exploration effort in human history, and we cannot get there. Not with any spacecraft that exists. Not with any technology currently under development. Not within any time frame that a human being or even a human civilization could meaningfully plan around. The comfortable language of next door and nearest neighbor serves a purpose in astronomy. It establishes relative position within a galaxy of 400 billion stars. It distinguishes the Alpha Centauri system from the vastly more distant stars that populate the spiral arms and the galactic core. In that relative sense, the description is accurate. Alpha Centauri is indeed the closest. But closest in a galaxy 100,000 light-years across is not the same as close in any sense a human being would recognize. Calling Proxima Centauri close is like standing in New York and calling Tokyo nearby, because it is the nearest major city across the Pacific. The statement is technically true. It conveys relative position, but it tells you absolutely nothing about the wall of ocean separating the two locations. And the ocean between us and Proxima Centauri makes the Pacific look like a puddle. Everything you have ever known, every place humanity has ever visited, every spacecraft we have ever launched, every signal we have ever sent exists within a bubble, so small compared to the nearest star that it barely registers on the scale. Our entire explored universe, from low Earth orbit to the surface of Pluto, from the trajectories of Pioneer and Voyager to the most distant communication signals we have ever transmitted, occupies less than 1,000th of the distance to Proxima Centauri. We have spent the entirety of the space age exploring our own front porch while the nearest house sits over the horizon, invisible and unreachable. And that nearest house is not even far by cosmic standards. It is the closest address on the block. What comes next reveals just how badly the distance punishes every attempt we have ever made to cross it. Let us start with the fastest human-made object currently leaving the solar system and see how it fares against the distance. We just established Voyager 1 is travelling at approximately 38,000 miles per hour. That velocity sounds impressive in everyday terms. It is roughly 20 times the speed of a bullet fired from a rifle. It is fast enough to cross the entire continental United States in under 5 minutes. If you could sustain that speed on a highway, you would circle the Earth's equator in just over 39 minutes. By any standard rooted in human experience, 38,000 miles per hour is extraordinarily fast. But the moment you aim that speed at Proxima Centauri, something terrible happens to the numbers. At 38,000 miles per hour, Voyager 1 covers roughly 333 million miles in a single year. That sounds like meaningful progress, until you remember that the destination sits 25 trillion miles away. Divide 25 trillion by 333 million, and you get approximately 75,000. That is how many years the journey would take. 75,000 years. Not centuries, not millennia, 75 millennia. To place that duration in context, 75,000 years ago, anatomically modern humans had only recently migrated out of Africa. The last ice age had not yet reached its peak. Agriculture would not be invented for another 65,000 years. Written language would not appear for another 70,000 years. The entire recorded history of human civilization, from the first Sumerian clay tablets to the phone or screen in your hand right now, fits inside the most recent 5,000 years. Voyager would need to fly for 15 times longer than the entirety of recorded history to reach the nearest star, and Voyager 1 is not even the fastest object humanity has launched. The Parker Solar Probe, which studies the Sun at extremely close range, has reached speeds exceeding 430,000 miles per hour during its closest solar approaches. That is over 11 times faster than Voyager. It is the fastest speed any human-built object has ever achieved relative to the Sun. If you could somehow maintain the Parker Solar Probe's peak velocity and point it directly at Proxima Centauri, the journey would still take approximately 6,600 years. That is still longer than the gap between the construction of the Great Pyramid and today. The fastest thing we have ever built, travelling at a speed so extreme that it could cross from the Sun to Earth in roughly 9 days, would need thousands of years of unbroken flight to reach a star that astronomers describe as close. New Horizons, the spacecraft that photographed Pluto in 2015, left Earth at a launch velocity of roughly 36,000 miles per hour, one of the fastest departure speeds ever achieved. Even at that pace, its travel time to Proxima Centauri would stretch beyond 78,000 years. The differences between these spacecraft velocities, numbers that seem significant in a solar system context, become almost meaningless against the interstellar gap. Whether you are moving at 36,000 or 430,000 miles per hour, the nearest star remains tens of centuries to tens of millennia away. Speed improvements that would revolutionize travel within the solar system barely register on the interstellar scale. It is as if you were trying to drain an ocean with different-sized teaspoons. A bigger teaspoon helps, but the ocean does not notice. This realization leads to an uncomfortable mathematical truth about the relationship between speed and interstellar distance. To reach Proxima Centauri within a single human lifetime, say 50 years, a spacecraft would need to travel at approximately 500 billion miles per year. That works out to roughly 57 million miles per hour, or about 8.5% of the speed of light. Even the Parker Solar Probe, the fastest object we have ever built, travels at only 0.06% of light speed. The gap between that record-breaking velocity and what the nearest star demands is not a factor of 2 or 10. It is a factor of over 130. We would need to make our fastest spacecraft more than 100 times faster just to bring the travel time down to a human lifespan. And even that barely qualifies as a success. Arriving at age 80 after launching at age 30 is not exploration. It is exile. Now let us look at what actually fills the 25 trillion miles between here and there. Because the emptiness itself is part of the horror, people sometimes imagine interstellar space as a slightly less crowded version of the space between planets. Perhaps there are stray asteroids drifting through, rogue comets tumbling past, interesting phenomena scattered along the route like rest stops on a highway. This image is wrong in almost every way. The interstellar medium, the material that exists between star systems, is the most vacant environment in the known universe, accessible to observation. Near Earth, even the hard vacuum of orbital space contains trace amounts of atmospheric gas, debris from satellites, and particles streaming outward from the Sun in the solar wind. Move past the planets and the solar wind thins out, but persists, carrying charged particles at hundreds of miles per second in a bubble called the heliosphere. The heliosphere is the Sun's sphere of influence. the region where our star's output dominates the local environment. Voyager 1 officially crossed the outer boundary of the heliosphere, called the heliopause, in August of 2012, becoming the first human-made object to enter interstellar space. What it found on the other side was striking in its barrenness. Beyond the heliopause, the density of matter drops to approximately 1 atom per 10 cubic centimeters in some regions. These are not complex atoms. They are overwhelmingly hydrogen, the simplest element, drifting alone through a vacuum so thorough that individual particles may travel for years without encountering another atom. The temperature of the interstellar medium varies by region, but can reach extremely low values, just a few degrees above absolute zero in the coldest pockets. There is no warmth from a nearby star, no solar radiation to power instruments, no material to collect or process. The environment between our Sun and Proxima Centauri is as close to true nothing as the universe permits. Scattered through this void are occasional wisps of interstellar dust, grains of silicate and carbon compounds so tiny that millions of them could fit on the head of a pin. These dust grains are not bunched together in visible clouds at the scales relevant to interstellar travel between nearby stars. They are spread so thinly that a spacecraft would encounter them only sporadically. But at high velocities, even a microscopic dust grain becomes dangerous. A particle the mass of a sand grain striking a spacecraft at 20% of the speed of light would release energy comparable to a small bomb. The void is not just empty. It is hostile to anything moving through it quickly enough to make the journey feasible. There is one large-scale structure that occupies part of the distance between our solar system and the stars, but it offers no comfort. The Oort cloud is a theoretical shell of icy bodies believed to surround the Sun at distances ranging from roughly 1,000 to 100,000 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. The outer edge of the Oort cloud, if it extends as far as models predict, would reach approximately 1.6 light-years from the Sun. That is a vast structure. Its outer boundary would mark the absolute limit of the Sun's gravitational dominion, the point where passing stars can pluck objects away from our system entirely. But the Oort cloud's vastness creates a false sense of progress for anyone thinking about interstellar travel. Reaching its inner edge from Earth would already require a journey of roughly 300 years at Voyager's current speed. Crossing it entirely would take an estimated 30,000 years. And after spending 30 millennia traversing this outermost shell of our own solar system, you would still be barely 1/3 of the way to Proxima Centauri. The Oort cloud does not bridge the gap between stars. It underlines how enormous the gap truly is. Our solar system's most distant outpost, a structure so far from the Sun that its members are only loosely gravitationally bound, still falls laughably short of reaching the nearest neighbour. The Sun's influence extends far, but the stars are farther. Between the outer edge of the Oort cloud and the corresponding outer reaches of Proxima Centauri's own gravitational influence lies a stretch of space that belongs to neither star. This no man's land is the true interstellar void. No planets orbit here, no comets follow long elliptical paths through this region, no dust clouds gather in detectable concentrations. It is space in its rawest form, governed only by the faint tug of distant galactic gravity and the inexorable expansion of the universe. A spacecraft crossing this region would be more alone than any object has ever been in the history of human engineering. No signal from Earth would arrive for years. No rescue mission could be mounted. No correction could be issued in time to matter. Whatever enters this void must survive on its own or not at all. The light-speed barrier compounds this isolation in ways that deserve closer examination, because the speed of light is not just a limit on travel, it is a limit on knowledge. We tend to think of light speed as a constraint on how fast a spacecraft can move, and it is. But it also constrains how fast information can flow. No signal, whether electromagnetic, gravitational, or any other form of energy, can propagate faster than light through the vacuum of space. This is not an engineering problem awaiting a clever solution. It is built into the geometry of space-time as described by general relativity, confirmed by over a century of experimental verification. Nothing travels faster. Nothing ever will, according to our deepest understanding of physical law. For interstellar distances, this creates a communication delay that transforms every interaction into an exercise in patience and trust. As we established, even a signal traveling at the speed of light needs over 4 years to cross this gap, and any round-trip exchange consumes approximately 8.5 years. But that abstract number becomes something far worse when you apply it to an actual mission. Consider what it means in practice. If a spacecraft arrived at Proxima Centauri and encountered an unexpected situation requiring new instructions from mission control, the earliest those instructions could arrive would be more than 4 years after the request was sent. By then, the situation would have evolved for over 4 years without any guidance from Earth. The spacecraft would need to handle every contingency, every malfunction, every decision autonomously. Mission control would function less like a command center and more like a historian, receiving news about events that occurred years in the past and issuing responses that would arrive years in the future. This communication lag also affects our ability to study the nearest star system remotely. Every observation we make of Proxima Centauri shows us conditions as they existed over 4 years ago. When astronomers detected flares erupting from Proxima Centauri's surface, those flares had already ended years before the light-carrying news of their occurrence reached our telescopes. When the James Webb Space Telescope imaged the candidate gas giant around Alpha Centauri A in August of 2024, it was observing photons that left the Alpha Centauri system in approximately 2020. The planet, if it exists, had already moved along its orbit for years before we even saw the image. We are always looking at the past when we observe the nearest star, and the nearest star is the least delayed object beyond our solar system. Every other star in the galaxy presents an even older picture. The universe does not allow us to see anything in real time beyond our own immediate cosmic surroundings. To make the distance feel visceral rather than abstract, it helps to shrink the entire picture down to something the human body can interact with. Forget miles and light years for a moment. Imagine the sun as a grapefruit sitting on a table in London. At this scale, where the sun is roughly 5 inches across, the Earth would be a grain of sand orbiting 43 feet away. Jupiter would be a marble about 225 feet from the grapefruit. Neptune, the outermost major planet, would be a small pea sitting roughly 1/4 of a mile from the table. Pluto would be an even tinier grain about 1/3 of a mile out. That 1/3 of a mile radius encompasses the entire planetary solar system. Every planet humanity has ever visited, every world we have ever photographed, fits within a walk you could complete during a lunch break. Now find Proxima Centauri on this scale. It would be another grapefruit. But this grapefruit would not be down the street. It would not be across London. It would not even be somewhere else in England. At this scale, with the sun as a grapefruit in London, Proxima Centauri would be another grapefruit sitting in Moscow, over 2,500 kilometers away. The entire solar system fits within that 1/3 of a mile radius. The nearest star sits in a different country, separated from our sun by the width of an entire continent. That is the ratio. That is what closest means. Every planet, every moon, every asteroid, every comet we have ever known occupies a space so small compared to the nearest interstellar distance that you could walk across it in minutes, while reaching the closest star would require a journey across Europe. This model also reveals something about the void itself that flat numbers struggle to communicate. In that 2,500 kilometer stretch between the grapefruit in London and the grapefruit in Moscow, there is almost nothing at astronomical scale. A few stray grains of dust representing Oort cloud objects in the first few hundred kilometers. Then nothing. An entire continent of emptiness. No grapefruits, no grains, no marbles. Just empty space represented by thousands of kilometers of European geography, with nothing in it that corresponds to any significant astronomical object. The isolation is not just about distance. It is about the absolute vacancy of the space you must cross. There are no stepping stones, no islands, no waypoints, just void. And yet, despite this punishing emptiness, the nearest star system keeps giving us reasons to want to go there. As we discussed, Proxima Centauri hosts confirmed planets. But the star itself is nothing like our Sun, and that difference matters enormously for any assessment of what those planets might be like. Proxima Centauri is a red dwarf, the most common type of star in the Milky Way. It is small, cool, and dim, radiating only about 1/6% of the Sun's luminosity. You could not see it without a telescope despite it being the closest star to Earth. Its habitable zone, the region where a planet could maintain liquid water on its surface, sits much closer to the star than Earth sits to the Sun. Proxima Centauri B orbits its star at a distance of roughly 4.7 million miles, completing a full orbit in just over 11 days. For comparison, Mercury orbits the Sun at an average distance of about 36 million miles. Proxima B is nearly 8 times closer to its star than Mercury is to ours. This extreme proximity creates a harsh environment. Proxima Centauri is a violently active star. Red dwarfs are fully convective, meaning hot material from their interiors churns all the way to the surface, generating powerful and unpredictable magnetic activity. Proxima Centauri erupts with stellar flares that can briefly multiply its brightness by several times. These flares blast nearby space with intense ultraviolet and X-ray radiation. A planet orbiting as close as Proxima B would receive regular doses of high-energy radiation far exceeding anything Earth experiences. Observations with the Atacama Large Millimeter Array have revealed that Proxima Centauri is active not just in visible light, but also in radio and millimeter wavelengths, indicating that its flare activity extends across the electromagnetic spectrum. These flares could strip a planet's atmosphere over time, sterilize its surface, or break down complex molecules necessary for life as we understand it. This means the nearest potentially habitable world orbits a star that may be actively hostile to life. The planet sits in the right temperature zone for liquid water, but it exists under constant bombardment from a star that behaves nothing like the relatively calm Sun we depend on. Whether Proxima B retains an atmosphere, whether that atmosphere could shield a surface from radiation, whether any form of biology could endure such conditions, these are open questions that cannot be answered from 25 trillion miles away. They require close observation, ideally from orbit around the planet itself. The kind of observation that the interstellar void currently makes impossible. The Alpha Centauri system as a whole presents an even more complex picture. Alpha Centauri A and B orbit each other at distances ranging from roughly 11 to 36 astronomical units, depending on their elliptical orbital phase. That mutual orbit creates a gravitationally dynamic environment where stable planetary orbits are difficult to maintain. Any planet orbiting one star must contend with periodic gravitational perturbations from the other. The candidate gas giant, detected by the James Webb Space Telescope around Alpha Centauri A, if confirmed, would challenge current models of planet formation in binary systems. Its existence would suggest that giant planets can form and survive in environments previously considered too chaotic. But confirming this candidate requires additional observations, and those observations can only be made from here, from inside our solar system, peering across the void with instruments that collect photons old enough to have been travelling since before the observation was planned. Every new discovery about the Alpha Centauri system sharpens the same paradox. The more interesting the nearest star system becomes, the more painful our inability to visit it. We can detect planets, we can estimate their masses and orbital periods. We can measure the flare activity of their host star. We can even attempt to image gas giants in habitable zones using the most sophisticated telescope in history. But we cannot resolve surface features. We cannot sample atmospheres. We cannot photograph landscapes. We cannot confirm the presence of water, life, or geological activity. All of that requires being there. and being there requires crossing a distance that defeats every mode of transportation humanity has ever conceived. The void between here and Proxima Centauri is not merely a distance to be covered, it is a wall, an enforcer, a physical boundary that prevents the solar system from having any meaningful material connection to even its nearest neighbour. Light can cross it, carrying information in both directions, but light alone cannot satisfy the scientific questions that the nearest star system now demands. We need to send instruments. We need to place sensors. We need hardware in orbit around another star. And the space between here and there says no, not yet, not with what you have. Maybe not ever, unless you fundamentally change what your civilization is capable of building. The interstellar void does not care about human ambition. It does not soften for compelling scientific targets or yield to emotional arguments about exploration and destiny. It simply exists. 25 trillion miles of functionally empty space separating our sun from its nearest neighbour, enforcing a quarantine so thorough that even our fastest machines would need geological time spans to cross it. Inside the solar system, we have learned to think of distance as a problem that engineering can solve. We built bigger rockets, we calculated gravity assists, we miniaturized instruments, we figured it out. The interstellar void is the first distance we have encountered that does not respond to these strategies. The solutions that conquered planetary distances are not merely insufficient for interstellar ones, they are irrelevant. A different class of technology is required, a class that mostly exists only on paper, in speculative engineering proposals and theoretical physics discussions. And the most ambitious of those proposals, the ones that dare to suggest we could actually cross the gap within a human lifetime, face challenges so severe that even their most passionate advocates describe them as generational problems, requiring decades of development before a single prototype could be tested. What those proposals look like, what they demand, and why even the boldest of them barely dents. The problem is where this story goes next. The most intuitive response to an impossible distance is to build something faster. This is the instinct that carried humanity from wooden sailing ships to steam engines to jet aircraft to rockets capable of reaching other planets. Whenever a gap seemed too large, we built a machine that could close it. The history of transportation is a history of relentless acceleration, each generation inheriting a faster world than the one before. So, when confronted with the 25 trillion miles separating us from Proxima Centauri, the natural question is straightforward. Why not just build a faster spacecraft? The answer begins with chemistry and ends with physics, and neither one cooperates. Every rocket that has ever launched from Earth operates on the same fundamental principle. You carry fuel. You burn that fuel. The burning fuel produces hot gas. The hot gas shoots out the back of the rocket at high speed, and Newton's third law pushes the rocket forward. This is chemical propulsion, and it has taken humanity to the moon, delivered robots to every planet in the solar system, and flung Voyager 1 beyond the heliosphere. It works. But it has a ceiling, and that ceiling is absurdly low compared to what the interstellar gap demands. The problem is called the tyranny of the rocket equation. To go faster, a chemical rocket needs more fuel. But more fuel means more mass. More mass means you need even more fuel to accelerate that additional mass. And that additional fuel adds even more mass, requiring still more fuel. The equation spirals. For every increment of speed you want to gain, the fuel requirement grows exponentially. To accelerate a modest payload to even 1% of the speed of light using chemical propulsion, you would need a fuel mass so enormous that it exceeds the mass of the observable universe. This is not an exaggeration. The mathematics are unambiguous. Chemical rockets cannot reach interstellar velocities, not because we have not built a big enough rocket, but because the chemistry of combustion cannot release enough energy per unit of mass to make the numbers work. You could build a chemical rocket the size of a galaxy and it would still not reach 1% of light speed with any meaningful payload. The approach is not merely impractical, it is physically excluded. This realization has been understood since the early days of rocketry. Konstantin Tsiolkovsky, the Russian scientist who first derived the rocket equation in 1903, recognized that chemical propulsion would never carry humanity to the stars. He understood that fundamentally different energy sources would be required. The question was always what those sources might be, and whether they could ever be harnessed for propulsion. The first step beyond chemical rockets is ion propulsion, which works by electrically accelerating charged particles and expelling them at very high velocities. Ion engines produce far less thrust than chemical rockets, so they cannot launch from a planet's surface. But they can operate continuously for months or years, gradually building up speed in the frictionless environment of space. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. The thrust was gentle, roughly equivalent to the weight of a single sheet of paper resting on your hand, but over years of continuous acceleration, it accumulated significant velocity changes. However, ion propulsion faces the same fundamental limitation as chemical rockets, just at a higher level. The spacecraft must carry its propellant, typically xenon gas, and that propellant has mass. For interstellar distances, even the improved efficiency of ion engines cannot escape the exponential fuel problem. The exhaust velocities of ion engines are roughly 10 times higher than chemical rockets, which helps enormously for solar system missions but barely registers against the interstellar scale. An ion-powered spacecraft might reach Proxima Centauri in something like 50,000 years instead of 75,000. An improvement, technically, but not one that changes the fundamental verdict. Ion propulsion is a solar system technology. It cannot cross the void. Nuclear propulsion represents a much larger leap. Nuclear reactions release roughly 1,000,000 times more energy per unit of mass than chemical combustion. In theory, this enormous energy density could produce exhaust velocities and thrust levels far beyond what chemical or ion engines achieve. Several nuclear propulsion concepts have been proposed over the decades, and some have come startlingly close to being built. Project Orion was the most audacious. Conceived in the late 1950s by physicist Ted Taylor and mathematician Freeman Dyson, Orion proposed detonating small nuclear bombs behind a spacecraft and riding the shockwaves. A massive pusher plate at the rear of the vehicle would absorb the force of each explosion, converting nuclear detonations into forward momentum. The concept was not subtle. It was propulsion by repeated nuclear explosions. But the physics worked. Calculations showed that an Orion-class vehicle could theoretically reach velocities of 3 to 5% of the speed of light, depending on design parameters. At 5% of light speed, Proxima Centauri would be reachable in roughly 85 years. Still not a single human lifetime, but within the span of a long, multi-generational mission, Orion was never built. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, effectively ending the project. The environmental and political consequences of launching a spacecraft powered by nuclear bombs were deemed unacceptable, but the engineering was sound. Dyson himself later reflected that Orion was not a fantasy. It was a real design that could have been constructed with 1960s technology. The stars were not beyond reach. They were beyond political will. Later nuclear concepts refined the approach. Nuclear thermal propulsion, which heats a propellant like hydrogen using a nuclear reactor and expels the hot gas through a nozzle, offers roughly twice the efficiency of chemical rockets. NASA tested nuclear thermal engines in the 1960s and early 70s under a program called NERVA, successfully ground-testing reactors that could have powered crewed missions to Mars. Nuclear thermal propulsion is excellent for fast transits within the solar system, but even doubling chemical rocket efficiency does not bridge the interstellar gap. The improvement is meaningful for reaching Mars in weeks instead of months. It is irrelevant for reaching Proxima Centauri. Nuclear fusion propulsion aims higher. Fusion, the process that powers the sun, releases energy by combining light atomic nuclei into heavier ones. A fusion-powered spacecraft could theoretically achieve exhaust velocities of several percent of light speed. The British Interplanetary Society designed a concept called Project Daedalus in the 1970s, a fusion-powered probe that would reach Barnard's star, roughly 6 light-years away, in approximately 50 years. Daedalus was enormous, a 2-stage vehicle massing over 50,000 tons, fueled by pellets of deuterium and helium-3 that would be ignited by electron beams in a series of controlled micro-explosions. The design was detailed and physically plausible, but it relied on fusion ignition technology that did not exist then and still does not exist in a form suitable for spacecraft propulsion. Controlled nuclear fusion remains one of the great unsolved engineering challenges. Decades of research and billions of dollars have brought us steadily closer, but a working fusion power plant on Earth has yet to produce sustained net energy output. Building a fusion engine compact enough, reliable enough, and powerful enough to propel a spacecraft for decades through the interstellar void remains far beyond current capability. Project Icarus, a 21st century update to Daedalus led by members of the British Interplanetary Society and the Tau Zero Foundation, revisited fusion propulsion with modern engineering knowledge. The study confirmed that fusion-powered interstellar travel is physically possible but remains technologically distant. Even the most optimistic timelines suggest that a fusion-powered interstellar probe could not be built before the late 21st century at the earliest, and likely much later. The engineering gaps are not small refinements awaiting clever solutions. They are fundamental challenges in plasma confinement, fuel production, materials science, and sustained autonomous operation that each represent decades of dedicated research. Antimatter propulsion occupies the extreme theoretical end of the spectrum. When matter and antimatter collide, they annihilate each other completely, converting 100% of their combined mass into energy. This is the most efficient energy release permitted by physics. By comparison, nuclear fission converts less than 1% of mass into energy, and fusion converts less than 1% as well. Antimatter annihilation dwarfs both by orders of magnitude. A spacecraft carrying even a few grams of antimatter could theoretically accelerate to a significant fraction of light speed. The problem is producing and storing antimatter. Current methods of antimatter production generate only nanograms per year at costs that run into trillions of dollars per gram. The total amount of antimatter produced in the entire history of human particle physics, if combined, would not be enough to power a light bulb for more than a few seconds. Storing antimatter requires keeping it perfectly isolated from all normal matter, because any contact results in instant annihilation. Magnetic containment systems can hold tiny quantities of antimatter for limited periods, but scaling this technology to the gram or kilogram quantities needed for propulsion is so far beyond current capability that it belongs more to the realm of theoretical physics than engineering. Every propulsion method that could theoretically cross the interstellar void faces the same pattern. The physics works. The engineering does not. Chemical rockets are excluded by mathematics. Ion drives are too slow. Nuclear thermal is insufficient. Fusion is plausible but decades away from the most basic prototype. Antimatter is centuries away from practical production. The propulsion technologies that could reach the nearest star exist on paper, in equations, in detailed engineering studies, but none of them exist in metal, in hardware, in anything that could be pointed at Proxima Centauri and launched. This is the landscape into which Breakthrough Starshot arrived in 2016, and its approach was radically different from anything that came before. Breakthrough Starshot did not try to build a bigger, faster rocket. It abandoned the rocket concept entirely. Instead, it proposed leaving the engine at home. The idea, based on theoretical work by physicist Philip Lubin at the University of California, Santa Barbara, was to build a massive array of ground-based lasers and use their combined light to push a tiny spacecraft across the interstellar void. The spacecraft would not carry fuel. It would not carry an engine. It would carry almost nothing at all. The entire probe, called a star chip, would weigh roughly 1 gram, about the mass of a paperclip. Attached to this gram-scale chip would be a light sail, a reflective membrane roughly 4 meters on a side, thinner than a human hair. The laser array on Earth would fire a coherent beam of approximately 100 gigawatts at the sail, and the pressure of that light would accelerate the tiny spacecraft to roughly 20% of the speed of light within approximately 10 minutes. The acceleration would be savage, on the order of tens of thousands of times the force of Earth's gravity, but the Starship, being so light, could theoretically survive it. Once the laser shut off, the Starship would coast at 20% of light speed, crossing the 4.24 light-years to Proxima Centauri in approximately 20 years. Not 75,000, not 6,000, 20. The breakthrough starshot concept promised to reduce the travel time to the nearest star from geological epochs to a single generation. A probe launched in the 20s or 30s could arrive at Proxima Centauri within the lifetime of the scientists who designed it. The concept was announced at a press event featuring Yuri Milner, the billionaire entrepreneur funding the project, alongside Stephen Hawking, who lent his voice and reputation to the effort. $100 million was pledged for research and development. The advisory board included some of the most prominent physicists and engineers alive. The ambition was clear. This was humanity's most serious attempt to design an interstellar mission. But ambition and feasibility are not the same thing, and the engineering challenges facing breakthrough starshot were staggering from the beginning. The laser array itself would need to produce 100 gigawatts of coherent power focused on a sail 4 meters across, at a distance of millions of kilometers. 100 gigawatts is roughly the total electrical generating capacity of a mid-sized country. Concentrating that power into a single coherent beam requires a phased array of lasers synchronized to extraordinary precision across a structure kilometers in diameter. No such laser array exists. No individual laser on Earth currently produces anything close to the required power. The engineering challenges of building, powering, and aiming such a system are immense, involving advances in laser technology, power generation, adaptive optics, and atmospheric compensation that would each constitute a major engineering achievement on its own. The sail must survive the acceleration phase. 100 gigawatts of laser power focused on a 16 square meter sail means the sail absorbs and reflects enormous amounts of energy. Even a tiny fraction of absorption, a fraction of a percent, would vaporize most known materials. The sail must be almost perfectly reflective at the laser's wavelength while remaining thin enough to be pushed effectively. It must also remain structurally intact, under accelerations that would crush any conventional material. Candidate materials include exotic crystalline films and dielectric metamaterials that exist in laboratories, but have never been manufactured at the required size or tested under remotely comparable conditions. The Starship itself must pack a camera, a power source, navigation systems, and a communication transmitter into a package weighing roughly 1 gram. While modern microelectronics are remarkably small and capable, building a fully functional interstellar probe at the gram scale requires miniaturization beyond anything currently available in commercial or military technology. The power source must function for over 20 years of cruise time, plus the active observation period at the target. The communication system must transmit data back to Earth across 4.24 light-years from a device the size of a postage stamp. The signal from such a tiny transmitter would be unimaginably faint by the time it reached Earth, requiring receiving dishes of enormous size and sensitivity. Calculations suggest that the sail itself might double as a communication antenna, but even so, the data rate would be extremely low, perhaps enough to transmit a few images over a period of years. Then there is the problem of interstellar dust. At 20% of the speed of light, the Starship would cover roughly 60,000 kilometers per second. At that velocity, a collision with even a microscopic dust grain would release enough energy to destroy the probe. The interstellar medium between the Sun and Proxima Centauri is thin, but it is not perfectly empty. Over 4 light-years of travel, the probability of encountering at least some dust grains is significant. Shielding the starship adds mass, which reduces the acceleration achievable by the laser, which reduces the final velocity, which increases the travel time. Every design trade-off pulls against the others. Despite these challenges, Breakthrough Starshot generated genuine excitement in the scientific community. For the first time, an interstellar mission concept had serious funding, institutional support, and a plausible physics foundation. Dozens of research grants were issued. Academic conferences convened to discuss specific technical problems. Prototype sprites, tiny chip-scale satellites, were successfully launched into orbit in 2017 and 2019 to test basic concepts. The project was not idle, but the pace of progress did not match the ambition. By 2025, Breakthrough Starshot had spent approximately $4.5 million of its $100 million pledge, funding roughly 30 research contracts. The project's founder, Yuri Milner, and its scientific advisors became increasingly difficult to reach for comment. A report on the project's status was promised for spring of 2025, but had not appeared by the time journalists went to press. In September of 2025, Scientific American reported that the project appeared to be on indefinite hold. There was no formal announcement of cancellation, no press conference to mark the end. The most ambitious interstellar mission ever seriously funded simply went quiet. The reasons for the stall are not entirely public, but the engineering timeline tells its own story. Building a 100-gigawatt laser array was never going to happen within a decade. Neither was developing a gram-scale interstellar probe with a functional camera and transmitter. Each individual technology required breakthroughs that could take decades on their own. Combining them into a working system, testing that system, and actually launching a fleet of starships toward Proxima Centauri was always a multi-generational project disguised in the optimistic language of a single-generation goal. The physics permits it. The engineering does not yet support it. The funding, while unprecedented for interstellar research, was still a tiny fraction of what the full development effort would eventually demand. Meanwhile, other interstellar propulsion concepts continue to be explored in academic papers and engineering studies. In 2025, researchers from Brown University and TU Delft published work on an ultra-thin light sail, optimized using artificial intelligence, pushing the boundaries of sail design closer to what Starshot would require. Separately, a study on using a relativistic electron beam instead of a laser to propel a much heavier probe, up to 1,000 kilograms, suggested that larger scientific payloads could potentially reach Alpha Centauri, though at the cost of even greater infrastructure requirements on the launch end. The Tau Zero Foundation continues to investigate fusion and beamed energy concepts. Academic research into interstellar travel is more active now than at any previous point in history, but active research is not the same as imminent capability. Every serious assessment of interstellar propulsion technology reaches the same conclusion. We are decades away from the most basic proof-of-concept hardware for any method capable of reaching the nearest star within a human lifetime, and we are likely a century or more from an actual launch. The nearest star is not waiting for us to catch up. It sits at 4.24 light-years regardless of our engineering timeline, and the distance does not shrink with effort. It only reveals new layers of difficulty the closer we look. There is a particular cruelty in the relationship between what we know about the nearest star system and what we can do about it. Our instruments have become extraordinarily precise. The NIRPS spectrograph can detect the radial velocity wobble of a star caused by a planet with less than 1/3 of Earth's mass orbiting it. The James Webb Space Telescope can block out the light of a star and search the surrounding space for the faint thermal glow of a planetary companion. These are astonishing capabilities that would have seemed like science fiction a generation ago. We can find planets around the nearest stars. We can measure their masses. We can constrain their orbits. We are approaching the ability to characterize their atmospheres by analyzing the spectrum of starlight filtered through them. But all of this is remote sensing. It is astronomy, not exploration. We are pressing our faces against the glass of a window and describing what we see inside a room we cannot enter. The planets of the Alpha Centauri system are real objects with surfaces, atmospheres, geological histories, and possibly even biospheres. We can infer broad properties from 25 trillion miles away. We cannot confirm details. We cannot resolve features smaller than entire hemispheres. We cannot taste the chemistry, feel the geology, or test the biology. Every major question about the nearest star system, whether Proxima b has retained an atmosphere, whether Alpha Centauri A's candidate planet is real, whether any of these worlds harbour conditions compatible with life, requires either dramatically better remote sensing or actual physical presence. And physical presence requires crossing the void. The tools we use to study the nearest stars are improving rapidly. The extremely large telescope, currently under construction in Chile's Atacama Desert, with a primary mirror nearly 130 feet across, is expected to see first light around 2028. It will carry instruments capable of directly imaging exoplanets around nearby stars and potentially analyzing their atmospheric composition through reflected starlight. NASA's Nancy Grace Roman Space Telescope, planned for launch as early as late 2026, will carry a coronagraph designed to test new technologies for blocking starlight and revealing orbiting planets. The Habitable Worlds Observatory, a future NASA flagship mission still in its conceptual phase, aims to be the first space telescope specifically designed to image Earth-like planets around Sun-like stars and search their atmospheres for signs of life. Each of these instruments will teach us more about the nearest star system. Each one will sharpen our picture of what exists just 4 light-years away, and each discovery will make the distance more painful, because the more we learn about the worlds next door, the more we will want to go there, and the harder we will slam against the wall of 25 trillion miles of empty space. There is a version of the future where Breakthrough Starshot or a successor program eventually succeeds, where a fleet of gram-scale probes accelerates to 20% of light speed and arrives at Proxima Centauri 2 decades later, where tiny cameras photograph a rocky world in the habitable zone of the nearest star and transmit those images back to Earth across 4 light-years of void. That future is physically possible. Nothing in the laws of physics prevents it. But even in that best-case scenario, the probe arrives after a 20-year journey, snaps pictures during a flyby lasting only a few hours because it is moving too fast to stop, and then continues past the system into deep space forever. The images take another 4 years to reach Earth. The entire mission from launch to data return spans roughly a quarter century, and the data it returns, while historic, would consist of a handful of images captured during a fleeting pass through a system that deserves years of sustained observation. Stopping at the nearest star is an even harder problem than reaching it. To decelerate a spacecraft from 20% of light speed to orbital velocity requires either carrying enough fuel to reverse the acceleration, which brings back the exponential mass problem, or using some form of braking at the destination. One proposed method involves using the target star's own light to decelerate a light sail by angling the sail to catch stellar photons. But Proxima Centauri is so dim that its light pressure is inadequate to brake a sail arriving at 20% of light speed. Alpha Centauri A and B are brighter and could theoretically slow a carefully designed sail, but the deceleration would take years, and the orbital mechanics of a 3-body stellar system enormously complicate the maneuver. Another concept suggests using a magnetic sail to interact with the charged particles in the stellar wind, gradually decelerating over a long approach. This method remains almost entirely theoretical, with no hardware demonstration of any kind. The tyranny of interstellar distance is not limited to the outbound journey. It infects every phase of the mission. Getting there takes decades. Communicating takes years. Stopping is harder than arriving. Sustained observation requires capabilities we cannot yet engineer at any scale, let alone at the gram scale that makes the journey possible. Each solution to one problem creates or reveals another. The distance is not a single barrier. It is a cascade of barriers, each one reinforcing the others, each one reminding us that the gap between star systems was not designed for crossing. Humanity has been building faster machines for 3 centuries. We went from horses to steam trains in a generation, from propeller aircraft to jets in 2 decades, from the first satellite to a moon landing in 12 years. This pattern of accelerating progress has conditioned us to expect that every distance will eventually yield to engineering. The nearest star is the first distance that has resisted this expectation completely. We have been aware of interstellar distances for over a century. We have been actively designing interstellar propulsion concepts for over 60 years. And the gap between our fastest technology and the minimum speed needed for a reasonable interstellar transit has not closed by any significant margin. The fastest object we have ever built still needs thousands of years to reach the nearest star. The most radical concept ever funded is on indefinite hold. The physics says yes. The engineering says not yet. And the distance does not wait. What this means for our understanding of where we stand in the cosmos, and why the nearest star rewrites our idea of isolation itself, is where this story arrives at its conclusion. Everything we have explored so far has been building toward a single realization, and it is not the one most people expect. The terrifying truth about the closest star to Earth is not simply that it is far away. Plenty of things in the universe are far away. The edge of the observable universe sits 46.5 billion light-years from Earth. The most distant galaxies we can detect emitted their light when the cosmos was less than 500 million years old. Compared to those numbers, 4.24 light-years sounds modest, almost trivial. The terrifying truth is something more specific and more personal. It is that the closest star, the very nearest point of light beyond our sun, the one object in the sky that represents the absolute minimum interstellar distance, already sits so far away that it defeats every form of transportation, communication, and intuition that humanity possesses. The terror is not in the big numbers, it is in the small one. 4.24 light-years is the shortest possible interstellar journey, and it is already impossible. This distinction matters because it redefines the meaning of the word isolation for our entire species. Inside the solar system, humans have spent decades building a network of robotic explorers, orbital telescopes, and communication relays that connect us to the worlds around our sun. We receive daily weather reports from Mars. We have mapped the surfaces of moons orbiting Jupiter and Saturn. We have tasted the geysers of Enceladus through the instruments of the Cassini spacecraft. We have collected samples from asteroids and returned them to laboratories on Earth. The solar system is becoming, slowly and with enormous effort, a known place. A space we inhabit, if only through our machines, and that expanding familiarity creates a psychological expectation that the next step outward will be more of the same. Farther, harder, more expensive, but fundamentally continuous with what came before. A natural extension of the same process that carried us from low Earth orbit to the outer planets. The nearest star demolishes that expectation. It tells us that the space between stars is not the next step on a smooth continuum. It is a wall, a discontinuity, a place where the rules governing exploration within a solar system simply cease to apply and a completely different regime takes over. The distances change by a factor of thousands. The travel times change by a factor of tens of thousands. The communication delays jump from minutes or hours to years. The energy requirements leap from enormous to functionally infinite with current technology. Every strategy that worked inside the solar system, gravity assists, chemical propulsion, remote operation from mission control, all of it fails at the interstellar threshold. Not gradually, not partially, completely. The nearest star is where the solar system ends and something else begins. Something colder, emptier, and more resistant to human presence than anything we have previously encountered. And this wall does not surround the solar system at some enormous distance. It begins immediately outside it, The Oort cloud, the outermost boundary of the Sun's gravitational domain, may extend to roughly 1.6 light-years. Beyond that lies the interstellar medium, and then Proxima Centauri at 4.24 light-years. The wall is not hiding somewhere deep in the galaxy. It is right here. The nearest star system presses against the outer edges of our own solar system's sphere of influence, close enough to study, close enough to characterize, close enough to tantalize, and far enough away to be completely unreachable. The cruelty is architectural. The universe placed a fascinating multi-star system with confirmed planets, including a rocky world in the habitable zone of the nearest star, just barely beyond the threshold of possibility. Near enough to know about, too far to visit. To fully appreciate what this means, consider what the solar system looks like from the perspective of the interstellar scale. At the distances that matter for reaching other stars, our entire planetary system is invisible, not small, invisible. The Sun would be a dim point of light, indistinguishable from thousands of similar stars in its galactic neighborhood. The planets, even Jupiter, would be undetectable without specialized instruments pointed at precisely the right location at precisely the right time. The asteroid belt, the Kuiper belt, the Oort cloud, the vast complex of worlds and objects that constitutes our cosmic home, all of it vanishes into a single unremarkable dot. From the nearest star, everything humanity has ever known or done occupies a space so compact that it would be lost in the background noise of the Milky Way. This is not a metaphor about humility. It is a geometric fact. The solar system occupies a volume that is infinitesimally small compared to the interstellar distances, separating it from even its closest neighbor. Every planet, every moon, every space station, every satellite, every signal we have ever transmitted exists within a bubble that registers as essentially zero diameter on any map drawn at the interstellar scale. We are not just isolated. We are dimensionally insignificant. The nearest star does not even need to be far away by galactic standards. To make our entire existence locally imperceptible, 4 light-years is enough. 4 light-years is already more than enough. The Fermi paradox, the famous question of why we have not detected evidence of extraterrestrial intelligence, is usually framed as a biological or sociological puzzle. Where are the aliens? Why have they not contacted us? Why does the galaxy appear silent despite the hundreds of billions of stars that might harbor technological civilizations? These are important questions, and they have generated decades of productive scientific and philosophical discussion. But the nearest star offers a more fundamental answer that does not require exotic solutions like great filters or self-destructive civilizations. The answer may simply be geometry. If the gap between our solar system and the nearest star is this difficult to cross, and if that gap represents the minimum interstellar distance, then every pair of neighboring star systems in the galaxy faces the same barrier. Every civilization that arises around any star confronts the same physics, the same void, the same exponential fuel requirements, the same light-speed communication delays. The galaxy contains 400 billion stars, and the average distance between neighboring stars in our region of the Milky Way is roughly 4 to 5 light-years. This means the Alpha Centauri gap is not an anomaly. It is typical. The standard spacing between stars throughout the galactic disk imposes the same impossible distances that separate us from Proxima Centauri. Every star system is an island. Every civilization, if civilizations exist elsewhere, is marooned. This reframing changes the character of the Fermi paradox from a mystery to an expected outcome. The galaxy might be full of intelligent species, each one confined to its own stellar neighborhood by the same distances that confine us. Radio signals transmitted by alien civilizations would weaken with the square of the distance, becoming undetectable against the cosmic background noise within a relatively small radius. Even a civilization that has been broadcasting for millions of years might remain invisible to receivers more than a few hundred light-years away, depending on the power of their transmissions and the sensitivity of our instruments. The galaxy could be teeming with life and still appear silent because the distances between stars enforce a quarantine that no civilization has overcome. To understand how thoroughly this quarantine operates, imagine two civilizations that have already found each other. Suppose a technological species around Proxima Centauri detected Earth's radio emissions and decided to respond. They aim their most powerful transmitter at our solar system and send a message. That message, travelling at the speed of light, arrives 4 years and 3 months later. Humanity receives it, confirms it is artificial, and begins composing a reply. Assume we respond within a single year, an optimistic timeline given the institutional and political complexities of crafting a message on behalf of an entire species. Our reply then travels another 4 years and 3 months back across the void. The first complete exchange, a single question and a single answer, has now consumed nearly a decade. Now extend that exchange into something resembling a conversation. Each additional round trip adds another 8.5 years at minimum. After 10 exchanges, nearly a century has passed. The individuals who initiated the conversation on both sides are dead. The institutions that managed it may have been restructured, defunded, or replaced. The languages used in the original messages may have evolved. The political and cultural context that motivated the exchange may no longer exist. A conversation between neighbouring civilizations separated by the minimum interstellar distance would unfold not across hours or days, but across generations. Neither side would ever know whether the other still existed at the moment a message was received. Every transmission would be an act of hope, directed at a correspondent who might have fallen silent years ago. This is not long-distance communication in any sense humans have experienced. It is correspondence with the past. Messages do not connect two living societies in real time. They connect the present of one civilization with the historical record of another. The conversation is always out of date, always lagging behind whatever has actually happened, always arriving too late to influence events that have already unfolded. And this is the best case. The nearest star, the shortest possible delay. Every other pair of civilizations in the galaxy faces longer gaps, slower exchanges, deeper isolation. Even successful contact between neighbouring star systems would feel less like a dialogue and more like reading letters from the dead. This does not mean interstellar travel is permanently impossible. It means that the default condition of any technological species is isolation, and that breaking out of that isolation requires a level of engineering ambition that may take centuries or millennia to achieve. The nearest star is the first rung on an interstellar ladder. Reaching it would represent the single greatest expansion of human capability in history. But even reaching it would only demonstrate access to the nearest island. The next nearest stars, Barnard's star at roughly 6 light-years, Wolf 359 at nearly 8 light-years, Lalande 21185 at about 8.3 light-years. Each one imposes its own version of the same barrier, slightly larger, slightly more demanding, but fundamentally identical in character. Reaching the nearest star does not open the galaxy. It opens one additional system. The galaxy remains vast, sparse, and uncooperative with anything travelling below a significant fraction of the speed of light. And yet, there is something in the human relationship with this distance that refuses to settle into despair. Because the same species that cannot currently cross 4.24 light-years has done something remarkable. It has measured that distance. It has identified the stars in the Alpha Centauri system, determined their masses, their temperatures, their compositions, and their orbital relationships. It has discovered planets around the nearest star and characterized their properties. It has detected stellar flares on Proxima Centauri, analyzed their energy output across multiple wavelengths, and assessed their implications for planetary habitability. It has aimed the most powerful telescope ever built at Alpha Centauri A and found a candidate planet orbiting in the habitable zone. It has designed, at least on paper, a propulsion system that could reach the nearest star within a human lifetime. It has launched a spacecraft that is about to achieve 1 light day of distance from Earth, the farthest any human-made object has ever travelled. None of these accomplishments crosses the interstellar void, but all of them demonstrate something about the species that produced them. We cannot go to the nearest star, not yet, but we have reached toward it with every tool we possess. We have measured it, catalogued it, analyzed it, and imagined vehicles to carry us there. The distance defeats our machines, but not our curiosity. It stops our hardware, but not our instruments. The nearest star is beyond our physical reach and entirely within our intellectual grasp. That contradiction defines humanity's current relationship with the cosmos more precisely than any other single fact. There is also a strange beauty in the architecture of this predicament. The universe is not uniformly hostile to knowledge. It allows light to cross the interstellar void freely. Photons from Proxima Centauri travel 25 trillion miles without significant degradation and arrive at Earth carrying detailed information about their source. We can analyze the spectrum of that light and determine what elements exist in the star's atmosphere. We can monitor the star's brightness over time and detect the flares that erupt from its surface. We can measure the star's radial velocity and infer the gravitational tugs of orbiting worlds. The universe permits observation across interstellar distances with remarkable generosity. It sends us information constantly, encoded in photons that cost nothing to receive. What the universe does not permit, at least not easily, is physical contact. We can look, we cannot touch. We can listen, we cannot visit. The cosmos has arranged itself so that knowledge flows freely across the void, while matter remains trapped near its star of origin. This arrangement might be a coincidence of physics, a consequence of the fact that photons are massless and therefore travel at light speed while spacecraft are massive and therefore cannot. But it produces a lived experience for any technological species that feels almost deliberately calibrated. You can know about the stars, you can discover their planets, you can dream of visiting them, but you cannot go, not without solving problems that may take your civilization centuries to master. The universe offers an infinite library but locks the doors to every room. This framing reveals something important about the nature of interstellar distance that pure numbers cannot capture. The gap between the solar system and Proxima Centauri is not just physically large, it is experientially transformative. It changes what exploration means. Inside the solar system, exploration is an activity conducted by machines under the direction of humans, operating on timescales of months to years, with communication delays of minutes to hours. Results arrive quickly enough to influence mission design in real time. The process is interactive, adaptive, alive with feedback. Interstellar exploration, if it ever becomes possible, will be nothing like this. It will be an act of faith conducted across decades, with results that arrive long after the decisions that produced them were made. A probe launched toward Proxima Centauri today, using the most optimistic technology projections, would arrive when the scientists who designed it are elderly or dead. Its data would reach Earth when the generation that launched it has been replaced by their children. Interstellar exploration is not an extension of solar system exploration. It is a fundamentally different human activity, requiring a relationship with time, patience, and institutional continuity that humanity has never demonstrated at the required scale. Consider the timescales involved even in the most optimistic scenario. A breakthrough Starshot-class mission, if all the engineering challenges were solved tomorrow, would launch a fleet of gram-scale probes that would arrive at Proxima Centauri roughly 20 years later. During those 20 years, the probes would be unreachable, unsteerable, and uncorrectable. They would fly through the interstellar medium at 60,000 kilometers per second, accumulating damage from cosmic rays and micrometeorites with no possibility of repair. Upon arrival, they would flash through the Proxima Centauri system in a matter of hours, capturing whatever data their tiny instruments could record during the flyby. The data would then take over 4 years to travel back to Earth at the speed of light. From launch to data return, roughly a quarter century would elapse. A generation of scientists would devote their careers to a mission whose results they might not live to see. Now compare that with the actual timeline for developing the technology. Even optimistic projections place the first possible launch of an interstellar probe in the second half of this century at the earliest. More realistic assessments push it into the 22nd century. The laser array alone requires advances in power generation, beam coherence, and atmospheric compensation that will take decades to achieve. The sail materials require nanotechnology breakthroughs that remain speculative. The star chip must be engineered to survive conditions no instrument has ever experienced. If development begins in earnest today, a working system might be ready by 2080 or 2100. The first data from the nearest star system would then arrive sometime around 2125 or later. These dates are not presented to provoke despair. They are presented to calibrate expectations. Reaching the nearest star is not something that will happen in the next funding cycle, the next administration, or the next decade. It is a civilizational project, a multi-generational commitment that would span longer than any single institution has yet survived in human history. The longest-running organizations on Earth, certain universities, religious institutions, and national governments have existed for roughly 1,000 years at most. An interstellar program would need to maintain focus, funding, and institutional memory for at least a century, and more likely several centuries, from initial research through development, launch, transit, and data return. No human institution has ever sustained a single engineering project on that timescale. The nearest star does not just challenge our technology, it challenges our organizational capacity as a species. And yet, this challenge may be exactly what makes the nearest star so important, not as a destination, but as a benchmark. The distance to Proxima Centauri is the universe's way of telling us what interstellar civilization requires. It is a test, posed not by any intelligence but by the geometry of space itself. Can your species sustain a purpose across centuries? Can you build machines that survive decades without maintenance? Can you transmit information across light years with instruments the size of postage stamps? Can you organize your society around goals that outlast individual lifetimes? The nearest star asks all these questions simultaneously, and it will not accept partial answers. Either you can cross the void or you cannot. The distance is binary. It does not grade on a curve. Standing on Earth today, looking up at a sky in which Proxima Centauri is too faint to see without a telescope, the honest answer to these questions is that we cannot. Not yet. We are a species that has mastered planetary distances, explored every major body in our solar system, photographed objects billions of light years away, and detected gravitational waves from colliding black holes. We are not lacking in ambition or intelligence or courage. We lack only the specific set of technologies that the interstellar void demands, and the institutional endurance to develop them across the timescales required. But there is a final perspective that the nearest star offers, one that transcends engineering timelines and propulsion physics entirely. It is a perspective about what it means to exist in a universe where the distances between stars are this large. Because the interstellar void is not a flaw in the universe's design, it is a feature. The vast spaces between stars are what allow stars to exist as stable, long-lived nuclear furnaces in the first place. If stars were packed close together, their gravitational interactions would destabilize planetary orbits, strip away atmospheres, and prevent the billions of years of calm evolution that life requires. The same distance that isolates us is the distance that protects us. The void is not just an obstacle, it is a shield. The interstellar gap that prevents us from visiting our neighbours is the same gap that ensures our sun burns steadily, our orbit remains stable, and our planet retains the conditions that made complex life possible. We are isolated because isolation is the price of existence. This is the deepest lesson of the nearest star. The universe is not built for easy travel between its points of light. It is built for stable burning, for long evolution, for the slow accumulation of complexity on worlds that are sheltered by distance from the chaos of a crowded cosmos. The 4.24 light-years between our Sun and Proxima Centauri are not an engineering problem to be solved and set aside. They are a permanent feature of the cosmic architecture, a spacing that reflects the fundamental physics of stellar formation, galactic structure, and gravitational stability. Stars are born from collapsing gas clouds that fragment into clumps separated by light years. That separation is set by the physics of the gas, the balance between pressure and gravity, the rate of cooling, and the angular momentum of the collapsing material. The distances between stars are not arbitrary. They are determined by the same laws that determine everything else about the universe, woven into the fabric of reality at the most fundamental level. When you look at the night sky and see thousands of stars, you are looking at thousands of islands separated by oceans that dwarf anything on Earth. Each star burns in its own pocket of space, surrounded by a mote of vacuum that protects it and everything that orbits it from the gravitational influence of its neighbours. Our Sun is one such island. Proxima Centauri is the nearest neighbouring island. The ocean between them is 25 trillion miles wide, and that ocean is not an accident. It is the reason both islands exist at all. This is the terrifying truth about the closest star to Earth. It is not that the nearest star is surprisingly far away. It is that even the nearest star, the absolute closest point of light beyond our Sun, already sits at a distance so extreme that it shatters every intuitive idea we hold about proximity, accessibility, and neighbourhood. The distance to Proxima Centauri is not an outlier. It is the minimum. It is the gentlest possible introduction to interstellar space, and it is already enough to strand us completely. Every other star in the galaxy is farther. Every other interstellar crossing is harder. The nearest star is the easiest case, and the easiest case is already functionally impossible with everything we currently have. We live in a galaxy of 400 billion stars. We orbit one of them. The next nearest one sits 25 trillion miles away, and between our star and that neighbouring star stretches a void so empty, so vast, and so thoroughly hostile to human-scale engineering that it constitutes the most formidable barrier our species has ever faced. We can see across it. We can send signals across it. We can dream about crossing it. We can even design machines that might theoretically survive the journey. But we cannot cross it. Not today. Not this decade. Probably not this century. The nearest star is close enough to study and far enough to be unreachable. And that combination is the defining feature of humanity's position in the cosmos. We are not lost in space. We know exactly where we are. We know what surrounds us. We know the names, masses, temperatures, and planetary companions of the stars in our neighbourhood. We have mapped our galactic environment with extraordinary precision. We are not ignorant. We are imprisoned, confined by distance to a single star system, able to observe the universe in exquisite detail, but unable to physically participate in it beyond our own narrow corner. The walls of our prison are not made of stone or steel. They are made of light years of vacuum, of the simple and implacable geometry of a universe in which stars are separated by distances that no human technology can yet cross. And the nearest wall, the thinnest barrier, the shortest distance to freedom, is 4.24 light years, 25 trillion miles, a number that sounds small and means everything. The closest star to Earth is the most terrifying number in astronomy, not because it is large by cosmic standards, but because it is small by cosmic standards and already large enough to trap us completely. Somewhere out there, 25 trillion miles from where you sit, a small red star is burning. It has planets. At least one of them orbits in a zone where liquid water could exist. It is the nearest star in a galaxy of 400 billion, and it might as well be on the other side of the universe. Because for now, and perhaps for a very long time, the distance between here and there is the distance between what we dream and what we can do. The closest star to Earth is not close at all. It is the beginning of everything we cannot yet reach.